Today we're going to be looking at how matter and energy are factors that involve everything in the universe, including atoms and atomic structure. So we're going to be covering kind of a large scale in a wide range of topics here. It starts off with John Dalton, who came up with the concept of atomic theory that just said, you know what, all matter is composed of atoms. That each of those atoms have some very basic properties that they all share. When we look here, we look a little bit further, we start talking about elements. That elements are composed of one type of atom. Compounds contain two or more elements. Now, most of our world are based on compounds that have combinations of elements that bond in different ways. But the key part to this is that atoms do not change their identities. They're just rearranged into different substances. So a thinking problem that we'll discuss in class is, where does carbon from a tree actually come from? In other words, where does the building block of it actually come from? Here's an example of a periodic table. Hopefully we had a chance to study this where atoms here are composed of three ingredients. We can talk protons have a positive charge, electrons have a negative charge, and neutrons with no charge. Protons and neutrons compose the nucleus of an atom, and electrons are in orbital shells that are located in specific locations on the outside of the atom itself. Here's a more specific, specific or advanced periodic table. This has the element name, it has the atomic number, it has the symbol, and it has the atomic mass. The atomic mass is the small number at the bottom that comprises the value of protons and neutrons within the atom itself. Here's an example: atoms and compounds of homogeneous materials composed of one element. A heterogeneous material is composed of two or more elements, called a compound. Right? An iron nail is made up of just iron atoms, and water is made up of hydrogen, oxygen, and hydrogen, or H2O, so two hydrogens per oxygen in this case. Here we're looking at how did atoms come about, and how did we start determining where things were? And it comes down to J.J. Thomson thinking that there were like raisins in a bun, and even though it was kind of the thinking was I mean, it's not right, but it began the thinking of what are the smallest subatomic particles? Where does everything kind of, if we start breaking it down into smaller and smaller pieces, how far do we go until we get down to the fundamental building blocks? Then there's this Rutherford guy who shot these charged particles. He started doing science and scientific testing and said, you know what, I'm going to fire these charged particles into this gold foil, and we're talking teeny tiny pressed foil. And some of the charged particles, the protons, actually bounced back. So essentially it was, this phrase is, it was as if you fired an artillery shell at a piece of tissue paper and it came back and hit you in the head. That something took place that blocked the passage of the charged particles, and that then became the nucleus of atoms. Here we talk about subatomic particles. Notice that a proton is tremendously more massive than an electron, to be precise, about 1,837 times more massive. And in this case, electrons, they don't have zero mass, but they're just significantly, or about 1/2000th the mass of that of a proton or a neutron, which are equivalent in atomic mass units. Here we have element number 2, helium, has 2 protons, 2 neutrons, 2 electrons. And we'll get into that here in just a moment, and that moment is here. Here we're looking at helium. We can make sure we understand that the atomic number is going to tell me the number of protons and the number of electrons, because all atoms are neutrally charged in their natural state. And then I can take the atomic mass minus the atomic number and come up with my number of neutrons. Here's an example of carbon atom. Just starting to talk about the electron shells. And this isn't a perfect model. This is just something that allows us to get it's kind of a starting point of looking at atomic or electron shells. Here I have carbon is element number 6. It has 6 protons, 6 electrons, and in this case 2 electrons want to fill the first electron shell, and therefore it has 4 left over, so 4 would be found in the next shell. Here's something we're going to be looking at with triboelectric series in charging of objects, and essentially it's saying this: when you rub 2 objects together, some of the electrons from one object are stripped from the object, and they're transported or kind of transferred into the other object. So therefore, if something gave up electrons, it has a net positive charge. And if something gained electrons, it has a net negative charge. Right? Conservation of charge is going to tell us that whatever was given up was received. So if 3 electrons transferred, some object has a net positive 3 or plus 3, then the object must have the other object that it gained must have a negative charge, a -3 charge. So here we're looking at the triboelectric series, that these objects up here have that are highest on the table tend to have a greater affinity to gain electrons. So these are going to end up with a net negative charge, and these at the bottom are going to end up with a net positive charge, because these are more likely to give up or lose. So if it gives up or loses electrons, it's going to be positive. If they gain electrons, they're going to be negative. Here we talk about the 4 primary forces in the universe. Electromagnetism is the force that we're focusing on in this unit. This is the force between charged particles, which we will be able to look at Coulomb's law here in just a few moments. And then there's a couple other forces that we're looking at. The strong nuclear force. This is the strongest force in the universe. This is what holds a nucleus together. It holds protons next to protons. So by definition, it's stronger than the electromagnetic force, right? So if it overcomes the repulsion electromagnetic force, it must be stronger than it. There's another force that takes place at really, really small, teeny tiny distances, and that's the weak force. And this is what holds an atom together in between, well, let's just say it affects the rate of decay. But that's not the scope and scale of this class. But then there's gravity, and gravity is kind of a cool one. Gravity is kind of cool because it's the only force that acts over large distances, and that makes it kind of unique. It's very weak and is definitely the weakest of all forces, but it's the only one that acts over large distances. And therein lies the starting point for this particular lecture on the basics of atomic structure, building blocks of the universe.